So now we will see how the voltage can be built up in a self-excited machine. If you take a separately excited machine, then what is going to happen? The field winding will be excited by a separate DC source, right? Separate DC source. So when the prime mover of this generator, it is rotated and the field winding is excited by a separate DC source, then the voltage will be generated in this generator, right? Now if you consider a self-excited generator, in the self-excited generator, the field winding is in parallel with the generator directly, okay? Now even if the prime mover is rotated, the prime mover of the generator is rotated, you can write G here. So if the prime mover is rotated, there is still no field, and if there is no field, how will a voltage be generated, right? What is the expression for generated voltage? This is equal to Eg is some constant K into phi into omega. K depends on the system parameters. Phi is the field flux and omega is the speed. So now how will you get the field in a self-excited generator? That is what we are going to discuss now. Voltage buildup in a self-excited generator. So first we will consider the shunt generator, where the field winding is in parallel to the armature. The field winding is going to have a residual amount of flux present in it. Now what is residual flux? If you remember, it is the magnetization of the core that will remain even after the excitation is removed, okay? Now this residual flux is going to help in generating a small amount of voltage first, okay? When the prime mover is rotated, then with the help of this residual flux, a small generated voltage will be present, and once a generated voltage is available, then the field winding will have a voltage across it, right? And once there is a voltage across it, the field current will start flowing. Field current IF. So what is happening here? The presence of a residual flux, okay? This is residual flux, and with the rotation of the prime mover, omega, it is going to result in a generated EMF, okay? The amount of EMF, magnitude of EMF will be small, but still it will be generated. Now once generated EMF is present, then what is going to happen? We get a terminal voltage, okay? So now this terminal voltage will appear across the field winding, right? We are talking about the shunt generator, so across the shunt winding we can take. And this will in turn result in a rise in the field current, right? The field current means that the field flux will increase, and an increased field flux will result in an increase in the generated EMF, okay? So this is like a positive feedback loop that is happening here. More the generated EMF, more the terminal voltage, more the field current and field flux, and then again more the generated EMF. Now where is the end point? It has to end somewhere, right? It will not go indefinitely. The end point will be the point where the core reaches saturation. Process will continue till core reaches saturation. So once the saturation is reached, then the increase in field flux will not result in too much increase in the generated EMF. So that was about the shunt generator. Now what about the series generator? In the series generator, the field winding, it is going to be in series with the armature, right? Now what is going to happen? Even in the presence of a residual magnetic flux and rotation, right? Phi, RES and omega, let us say they are present. Then what is going to happen? The generated EMF will occur. The magnitude will be small, but it will still be present. But the generated EMF, will it lead to the field current? You can see that in a series generator, unlike in a shunt generator, this is not forming a field winding, is not forming a closed circuit unless until there is a load attached to it, right? So only when a load is attached can the field current flow in the presence of this small generated EMF. So having a load is a necessary condition for voltage buildup in a series generator, okay? Now once the load is connected, then everything else is the same. what is going to happen? Generated EMF will give rise to the field current. So we can take it as field current, armature current, or even load current, right? Once the field current is going to increase, then the field flux will also increase, and once field flux increases, then generated EMF will in turn increase. This again, the process is a positive feedback loop, and it will continue till the saturation of the core. What about compound generator? In a compound generator, it is the same kind of windings. There is a shunt winding and a series winding. Only difference is that both of them are present. Okay. Mechanism is going to remain the same. The mechanism of voltage build-up. Now we will see a few differences between the shunt and series winding. In a shunt winding, what is going to happen? The amount of current that will flow is less. Now why is that the case? If you consider this is the armature and the shunt winding is in parallel. Now here armature current flows and here field current flows, and this will be the load current. Now if the field current is too much, then the load current will be reduced. We don't want that. So we want field current to be at minimum. But if current is minimum, what is going to happen? The strength of magnetic field is going to be less. So what we do is we increase the number of turns. Number of turns is high for a shunt winding. In comparison, what is going to happen in series winding? In series winding, the same current will flow in the armature, in the field winding, and the same current is going to go to the load. Okay, and the load current will be of considerable magnitude. So the current, the field current that is flowing in the series winding, it is going to be high enough. So you can write here the field current is low in a shunt winding, in a shunt generator, and the field current in the series winding is going to be high. Okay, so less number of turns is sufficient in order to produce a field, a strong enough field. This is one difference, and the second difference is the thickness of the wire. As I have already told you, the shunt current, the shunt winding should have lesser field current, right? So that more load current flows. More amount of armature current is contributed towards the load side instead of to the shunt side. So what is going to happen? We are going to make use of a thinner wire. What will happen if you use a thinner wire? The area of cross section is going to be less, and lesser area of cross section implies that the resistance is high. This will ensure that the field current is kept minimum. And what about the case of series winding? In series winding, the current anyways it is going to be high. So what we don't want here is the unnecessary voltage drop here across the series winding. So in order to do that, what you have to do, you have to reduce the resistance. That means you have to use a thicker wire. Thicker wire will ensure that the area of cross section is increased so that the resistance is reduced. Okay, so this will ensure that voltage drop across the series winding is not too much because of high field current. Okay, so these are the two differences between the shunt and series winding.